This slide on the topic of semi-empirical method. Definition for semi-empirical methods. Semi-empirical methods are simplified version of Hartree-Fock theory using empirical or derived from experimental data. Corrections in order to improve performance. Semi-empirical is partially empirical or partially theoretical method. Semi-empirical methods are experimental data or the results of an ab initio calculations to determine some of the matrix elements or integrals. Semi-empirical quantum chemistry attempt to address two limitations, namely slow speed of calculation. The second, to overcome low accuracy of the Hartree-Fock calculation by omitting or parameterizing certain integrals based on experimental data, such as isomerization energy of atoms and or such as dipole moments of molecules. Advantage. As a result, semi-empirical methods are very fast, applicable to large molecules, and may give accurate results when applied to molecules that are similar to the molecules used for parameterization. Failure. On the downside, accuracy of the semi-empirical methods is erratic on many systems. Modern semi-empirical models are based on the neglect of diatomic differential overlap method or NDDO method, in which the overlap matrix S is replaced by the unit matrix. This allows one to replace the Hartree-Fock circular equation. Determinant H minus E is equal to 0 is replaced with a simple equation like a determinant of H minus E equal to 0. Existing semi-empirical models differ by the further approximations that are made when evaluating 1 and 2 electron integrals, and by the parameterization philosophy. Semi-empirical NDDO models are MNDO, AM1, PM3, and PDDG, PM3 methods. The MNDO has been quantified from the NDDO method. MNDO stands for modified neglect of diatomic overlap. Was found by Michael Dewar and Walter Thiel in year 1977. MNDO is the oldest NDDO-based model that experimental or parameterized of the following term. The first, one center two electron integrals based on spectroscopic data or isolated atoms. And the second, evaluates other two electrons integrals using the idea of multiple interactions from classical electrostatics. A classical MNDO model uses only S and P orbital bases, while more recent MNDO/D adds d orbitals that are especially important for the description of hypervalent sulfur species and transition metals. The MNDO has a number of known deficiencies such as inability to describe the hydrogen bond due to a strong intermolecular repulsion. The MNDO method is characterized by a generally poor reliability in predicting heat of formation. This is a disadvantage. MNDO method is described by Lutan-Hall equations for a closed shell system. The Lutan's equation Fc equal to SCE, where F is a Fock matrix, S is an overlap matrix, C is the matrix of the expansion coefficient, and E the energy matrix. Fock matrix F mu nu can be obtained using the equation 5.2 is equal to the Hamiltonian H core mu nu, which is equal to the integration as shown in equation 5.4 plus the summation lambda equal 1 to k, summations sigma 1 to k of the p lambda sigma, which is the density matrix as shown in equation 5.3, multiplied with the function as shown in the equation 5.2. Equation 5.4 is the energy of a single electron of the field of bare nuclei. To discuss the semi-empirical methods, it is useful to consider the Fock matrix elements in three groups. The one F mu mu, which is the diagonal elements. The second F mu nu, where mu nu are on the same atoms. And F mu nu, where mu nu are on different atoms. The Fock matrix elements, three groups, can be obtained as following equation. The first group, the Fock matrix elements, can be obtained using the equation 5.5, where H core mu mu can be calculated from equation 5.6. The second group, F mu nu is equal to H core mu nu, and pass the term as shown in equation 5.7, where the H core mu nu is equal to minus summation b not equal a of the v mu mu b, as shown in equation 5.8, where mu and nu are on A or on the same atoms. The third group, F mu nu, can be calculated using equation 5.9, where H core mu nu is equal to 1 over 2 S mu nu, and function of the summation of beta mu plus beta nu, where mu is on A and nu is on B atoms. Majority of expressions for the calculation of the Fock matrix resemble the expression for NDDO method. The main improvements are in the terms V mu mu B, V mu mu B, and the expression H core mu nu, which is now calculated using the overlap matrix mu nu. V mu mu B and V mu nu B are two centers. One electron attractions between an electron distribution phi mu mu or phi mu nu, respectively, on atom A and the core atoms B. These are obtained as the value of V mu mu B and V mu nu B form the equation 5.11 and 5.12 respectively. The expression for the core repulsion term is as follows. EA can be computed using the equation 5.13. AM1 method. AM1 stands for Austin model number 1. Was found by Michael Dewar and co-workers in years 1985. AM1 takes a similar approach to MNDO in approximating two electron integrals, but use a modified expression for nuclear core repulsion. The modified expression results in non-physical attractive forces that mimic van der Waals interactions. The modification also necessitates reparameterization of the model which was carried out with a particular imprecise and dipole moments, ionization potentials, and geometry of molecules. While this allows for some description of the hydrogen bond, as a deficiency such as systematic overestimates of basicity remain. Also, the lowest energy geometry for the water dimer is predicted incorrectly by the AM1 model. On the other hand, AM1 improves nicely some property, such as heat of formation over MNDO method. The AM1 The MNDO method tends to overestimate repulsion between atoms that are separated by distance equal to the sum of their van der Waals radii. AM1 method solves this by modifying the core term of the MNDO by a superposition of Gaussian functions. The expression for the new core term is shown in equation 5.14. PM3 methods. PM3 stands for parametric method number 3. Was found by James Stewart. PPM3 uses a Hamiltonian that is very similar to the AM1 Hamiltonian, but the parameterization strategy is different. While AM1 method was parameterized largely based on a small number of atomic data, PM3 is parameterized to reproduce a large number of molecular properties. This results in serious problems when analyzing intermolecular interactions, such as the calculation for the methane molecule, which is predicted to be a strongly bound dimer, which is erratic, or calculation for conformations of flexible molecules, such as the interaction of hydroxy is strongly attached to methyl in one pentanol. The accuracy of thermochemical predictions with PM3 is slightly better than that of AM1. The PM3 model has been widely used for rapid estimation of molecular properties and has been recently extended to include many elements, including some transition metals. PDDG/PM method stands for pairwise distance directed Gaussian of PM3 method. was found by William Jorgensen and co-workers. This method is to overcome some of the deficiency of the earlier NDDO-based methods by using a functional group specific modification of the core repulsion function. The PDDG modification provides good description of the van der Waals attraction between atoms, and the PDDG/PMC method appears to be suitable for calculations of intermolecular complexes. Furthermore, careful parameterization has made the PDDG/PM3 model very accurate for estimation of heat of formation. However, some limitations common to NDDO methods remain in the PDDG/PM3 model. The conformational energies are unreliable. Most activation barriers are significantly overestimated, and the sky of radicals is erratic. So far, only carbon atom, nitrogen, oxygen, hydrogen, sulfur, phosphorus, and silicon atoms, and halogen has been parameterized for PDDG/PM3 method. The NDO type methods, the most popular semi-empirical methods for studying ground states potential surfaces, are based on the MNDO model. The MNDO model in its current standard implementations as the method of the MNDO M1 and PM3 has been parameterized primarily with respect to ground state properties, with particular emphasis on the energies and geometry of organic molecules. The most frequently used methods, MNDO, AM1, and PM methods, are all based on the NDDO integral approximation. Summary: quantum chemical calculations can be separated into two main computational approaches. The first is an ab initio calculation. This includes the HF or Hardy-Fock calculations, include the MP or molar process perturbation theory calculations, and the FT or density functional theory calculation. The second computational approach is the semi-empirical methods. Semi-empirical methods is parameterizing certain integrals based on experimental data for being very fast, applicable to large molecules. It may give accurate results when applied to molecules that are similar to the molecules used for parameterization.